Okay, hi, now welcome to the video on halogens, which in case you didn't know are the group 7 elements. So this is every element that we see in this group here, including fluorine, chlorine, bromine, iodine and astatine at the bottom. Now the most important ones that you study are chlorine, bromine and iodine, and that's because they react in very similar ways, but there are differences of course. Fluorine is extremely reactive, and so we don't really study its reactions much, and astatine is radioactive, and so it disappears within minutes. Okay, so diving straight into the properties of the halogens. Now, the first property of the halogens is that they are all poisonous. Okay, not very nice, but they're all poisonous, and so we have to be very careful when we're handling them. They are all non-metals. Okay, they're on the right-hand side of the periodic table, which means they are the non-metals. And when they are turned into a gas, not only when they're a gas, but especially when they're a gas, they all have coloured vapour. Okay, so they all have colour when they are a gas. Now, just like almost all the other non-metals, they are covalent compounds. Covalent elements, not compounds. Covalent elements. And they have low melting points. So low melting points and boiling points. Okay. Now, when I say covalent, this means that they form simple molecules. So they form simple molecules. And remember, covalent bonds are the bonds which hold molecules together. For example, if I had a chlorine molecule, chlorine exists as Cl2, as do the rest of the halogens. That is a chlorine covalently bound to another chlorine. Now, I'm sure you could do that as a dot and cross diagram as well, but I've only represented it in this form for simplicity. But this obviously represents a covalent bond. Okay, now as we go down the group, okay, so if we had fluorine, chlorine, bromine, iodine. Okay, moving down the group, let's do this in a different colour. As we move down the group, okay, the melting and boiling points, so I'm just going to write MP and BP for short. MP and BP increase. Okay, they increase. And that is because as we go down, the atoms themselves are getting larger, which means in turn the molecules are larger. If the molecules are larger, we have greater intermolecular forces. Okay, so remember an intermolecular force is a weak force. It's not a covalent or an ionic bond, which are very strong, but it's a weak force of attraction between the atoms or the bonds in molecules. Okay, so if I had fluorine, fluorine is a very small atom. Okay, so let's say I had fluorine bound to another fluorine. Now, another one of these, fluorine, is going to feel some weak attraction. So a weak attraction, which I'm just going to draw here in yellow, to the other molecule, okay? And those are the intermolecular forces. So those there are the intermolecular forces. Now, on the flip side, if I had iodine, now iodine is way bigger than fluorine. Now this is not to scale, iodine is even bigger in comparison to fluorine, but we're just going to draw it like this so you get the idea. Now iodine obviously travels around as molecules as well, but the intermolecular forces, as you can see, there's a way larger area for them to act because of the size of the iodine, okay? And this means that even though these are still weak intermolecular forces, these ones, okay, in the iodine are going to be greater in strength than the ones in the fluorine. So therefore, iodine has a higher melting and boiling point than fluorine does. Iodine is a solid at room temperature. Solid at room temperature, I'm just going to say RT, okay? Fluorine is a gas at room temperature. Okay, and so that's, at room temperature. That shows you the difference between the two. Okay, now let's have a look at some of the reactions of the halogens. Okay, so the reactions. Now, the halogens are all in group 7, which means they all have 7 electrons in the outer shell. Okay, so 7 electrons, I'm just going to say E minus, in outer shell. Now, to get the noble gas configuration, they need 8 electrons in the outer shell. So these halogens need to obtain 1 electron. Now, what will determine how reactive the halogen is how easily they can obtain the electron. And I don't want to spend too much time on this, but if you have a look at the periodic table over here, fluorine, which is at the top, okay, I've drawn a square around it there. Fluorine only has 2 shells, okay? It's got the first shell and then the second shell, which it wants to fill up. This shell is relatively close to the positively charged nucleus of fluorine, and so electrons are attracted to it. They are attracted to it very strongly, and so fluorine can obtain an electron very easily, and so it is extremely reactive. It's actually the most reactive element known to humans. Okay. Now, as we move down the group, they all still need to obtain 1 electron. But if we have a look at iodine, iodine has many shells. So it has the first inner shell with 2 electrons. Then it has 1, 2, 3 electrons, which are 3 electron shells, which are full, and its 4th one here. Okay, so the 5th shell in total needs to obtain 1 more electron, and so that means that the electron shell is really far away from the nucleus, and therefore it's harder to attract electrons. It can still do it, but it's harder, and so iodine is not anywhere near as reactive as fluorine. Okay. Now, that is demonstrated with how they react, firstly, with hydrogen. Okay, so with hydrogen. Now, let me draw up an example. So the halogens, I'm just going to call them X for the moment, okay? So this X2 represents any halogen, plus hydrogen, okay? Both of these will be gases. Okay, even the bromine and the iodine, which aren't gases at room temperature, we're looking at this reaction if they were gases. Okay, they will form hydrogen, halogen. Okay, and so this will also be a gas. And to balance, we have 2 of those. Now, for example, if this X was chlorine, you would have chlorine gas plus hydrogen gas makes hydrogen chloride gas. So that would be HCl in that case. Okay, any of the other halogens, you just swap it. For example, hydrogen fluoride, hydrogen iodide, hydrogen bromide. Okay. Now, the reaction conditions required for this reaction tell you the story of how reactive the halogens are. So when we are using fluorine, this reaction is explosive even at negative 200 degrees Celsius and in darkness. So what this is basically saying is you're not really providing any energy to this reaction externally. The fluorine is reactive enough for this to just happen. And not just happen, it will be explosive. Okay, chlorine is the next most reactive, and this reaction is explosive in sunlight. So we're providing light energy in this case. Okay, but if we take away that light energy, it is slow. So it's slow in the dark. Okay, so explosive in sunlight, but in the darkness it's slower. Now, as we go down, we get even less reactive. We have bromine. Now, bromine requires a 300 degrees Celsius temperature plus a platinum catalyst. Okay, and you'll remember that a catalyst is something which will speed up a chemical reaction without itself being used up in the reaction. Okay, so we need a catalyst this time to make this reaction work. Now, finally, iodine. This reaction at 300 degrees Celsius plus our platinum catalyst. Okay, so we still add the platinum catalyst. It is still very slow. And it is also reversible. Let me just move this to the middle. You can see, reversible. Sorry for this bad handwriting. Okay, so it's a very slow reversible reaction at 300 degrees Celsius and with a catalyst. Whereas at negative 200 degrees Celsius and in the darkness, no catalyst, and in the darkness, it is explosive with fluorine. Okay, so that demonstrates quite nicely the difference in reactivity. Okay, something important here is that in this reaction, you have hydrogen and the halogen. They are both non-metals. Okay, both non-metals, which means that that is a covalent compound. Okay, so the hydrogen halide, or the hydrogen, not halide, that's ionic. The hydrogen plus halogen makes a covalent compound. Okay, now if the halogens react with a metal, so with metal, we form ionic compounds. Okay, and normally they are referred to as salts. For example, one you will have heard of is sodium, which is a solid, plus chlorine gas, okay, is going to give you sodium chloride. That is a solid, it is table salt, okay? Now balancing these, I would need 2 of those and 2 of those. But that is a metal reacting with the halogen to form an ionic compound, because we have a metal plus a non-metal. This forms an ionic compound. Okay, so finally what we're going to have a look at is displacement reactions. So displacement. Now you'll have heard this term before, and it is very similar to the displacement when you're using metals in the reactivity series. Basically the same thing. The more reactive halide or halogen, so a more reactive halogen, which is just a group 7 element, will displace a less reactive halogen from a solution of its salts. Okay? So what we produced before, the ionic compound up here, for example, sodium chloride, that is an example of a salt, and so this needs to be the case. Now, let me give you an example. If we had potassium bromide, now this is an ionic compound because we have a metal plus a non-metal. Okay, so potassium bromide, but remember it is in solution, so it is aqueous. Now if we add to that chlorine, okay, chlorine in solution, because this is all happening in solution. Now chlorine is more reactive than bromine. We learnt that earlier in the video. And so it will displace bromine from its salt. And we will form potassium chloride. And we have displaced bromine, so we will have bromine on its own. So these are all still in solution. All of this has happened in solution. And so this is what we get. Now we would have to balance because we've got 2 chlorines and 2 bromines. So that means that we would need in total 2 of these and 2 of these salts to make this balanced. Now, what would happen if I had this scenario? Bromine plus sodium fluoride. Now, both in solution. Now, pause the video and see if you can come up with an answer. Okay, so I hope you had a go. Well, what would happen is you would think that you would get sodium bromide plus fluorine, all in solution. But this is not the case. So no, doesn't happen. Let's cross that out. That is because fluorine is more reactive than bromine. So I didn't put a 2 here on the bromine, but it's Br2, not just Br. Bromine is less reactive than fluorine. Fluorine's more reactive than bromine. So bromine doesn't have the power. It's not reactive enough to boot fluorine out of its salt. Fluorine is way stronger and it will stay in its salt, and bromine can't do anything about it. So if you added bromine to sodium fluoride, you would see no reaction. So there would be no reaction. Okay, and that is what you would say. You wouldn't be able to see anything in the solution because no reaction has formed. There's not going to be a color change, and that is it. Okay, now I hope this has helped. If you do have any questions on the halogens, please do feel free to send me a direct email or comment in the box below, and I'll be sure to get back to you. But if this video has helped, please do give me a like and a subscribe, and I look forward to seeing you in the next video.